All right, I want you to study this guy's face carefully because I want you to remember this guy at the end of the lecture. I want to be able to remember his face, if not his name. All right, so how do you guys pronounce his name? Most of you guys pronounce it as Philip Leonard. That's not the proper pronunciation of his name. It's Philippe Leonard. He's almost silent at the end. This guy is German. This guy is a German physicist who wins the Nobel Prize in 1905 for discovering something called the photoelectric effect. All right, so he discovered something called the photoelectric effect in 1905. Nobel Prize is one of the highest accolades you can earn, not only for yourself, but for your country as well. It's a huge thing, kind of like soccer is outside of the United States. If you're in the United States, of course, you're completely clueless. As long as you love Kim Kardashian and her lovely little ass, you're perfectly fine. All right, so 1905, this guy wins the Nobel Prize for something really simple. He discovers something extremely simple. This is the sort of shit that they used to discover 100 years ago, and they used to get a Nobel Prize for. And so you shine light onto a metal surface, and you generate electricity. These are known as photodiodes today. So this guy discovers it by chance. So he shines light onto a metal surface, and then the electrons come out jumping. It's called photoelectric effect. Years 1902. Eventually, this is recognized as a huge discovery to an extent that he wins the Nobel Prize in 1905. But no one knew why the light would just liberate these electrons from metal surfaces. Why is it that when you shine a light onto a metal surface, the electrons will come out jumping? Mystery. It's one of the mysteries in physics at the turn of the 20th century. Another mystery, which was persisted nearly a century, and this is from the 19th century. Whenever you heat something up, at some point that something is going to glow, and when it's glowing, at first it's going to glow in red, and when you increase the temperature, there's going to be a shift in color towards the blue end. Why is that things when they're heated, they will glow in red, and then when the temperatures are increased, there's going to be a shift in color towards the blue end? It was not understood. This is known as the blackbody radiation. So the blackbody radiation is what happens when things are heated. All right, so they will glow at first, and then when they're glowing, initially they will glow, generating red. And when you increase the temperature, there would be a shift in color towards the blue end. So what's causing the shift in color from red to blue when things are heated? So this was a mystery. Guys, this was a mystery that lasted almost a century. No one knew how to actually answer this. Another mystery in physics is something that we discussed last week. So what breaks light into its color components? So you got the white light going through a prism. Red is going to be on top, the blue is going to be at the bottom. So here's what we know so far. Red is going to move faster than blue. But the question is why? Why is it that the color red, higher wavelengths, are moving faster than the shorter wavelengths through the material? So that's another mystery, which was not understood. So the white light is going to break down into its color components. So it's going to give you the color spectrum on the screen. On top of that, if you change your light source to hydrogen, it's going to give you 4 spectral lines. So these are known as the spectral lines of the hydrogen atom, or line spectrum. So you end up getting 4 different colors corresponding to 4 different frequencies. Notice that you will get 2 shades of violet, combination of blue-green, and you will get red. So you will end up getting 4 different colors. 2 shades of violet, combination of blue-green, turquoise, or red. So those are the colors that we end up getting. So how many spectral lines generated by the hydrogen atom within the visible spectrum? This is known as the Balmer series. So you end up getting 4 different colors. All right, you need to remember the colors. We end up getting 2 shades of violet, combination blue-green, and then we will get red. And this is known as the Balmer's series. All right. So hydrogen atom is going to give you 4 spectral lines. So the question is where? What's happening inside the hydrogen atom that's going to give us 4 different spectral lines, 4 different frequencies of color? So this was a curiosity, and people, physicists were pondering about it for years on end. And so about 50 years later, this guy, his name is Balmer. This guy is actually a mathematics professor at a nursing school. This is happening during the 18th century, obviously. Life is boring. So this guy, in order to make his life a little bit more interesting, decided to actually tackle this puzzle and came up with a mathematical formula. So the mathematical formula kind of looks like this, somewhat looks like this. Actual formula looks more like this. All right, so he comes up with this. F here is going to represent the frequency of the line that you're looking at. Remember, you got 2 shades of violet, you got a combination of blue-green, and you got red. C is the speed of light. R is a constant. This is known as a Rydberg's constant, so that's a huge number. And you have 2 squared in the denominator, and you have n here. So n is the one that we will get to focus on. So the formula that I'm describing is the same as this formula that you're looking at. So this n is the one that we will focus on. So what does n represent in the Balmer's series? All right, so it's so happens n is just a number. It could be 3 as long as it's bigger than this. It's going to give you the correct frequencies. If it's 3, it'll give you one of the frequencies. It can be 4, it could be 5, and it could be 6. So if n is 3, it's going to give you the color red. All right, in the Balmer series. All right, so it's going to give you the color red. If it's 4, it's going to give you a combination of blue green. If it's 5 and 6, it's going to give you 2 shades of violet. That's it. So n is a mysterious number, and this is a mysterious formula because somehow using this formula, you can generate the corresponding frequencies of the hydrogen spectrum, hydrogen atom spectrum. That's what you end up getting. So if n is 3, what do you end up getting? You get the frequency for red. 4, you end up getting the frequency for blue-green. 5 and 6, it's going to give you 2 shades of violet. All right, so it's known as an empirical formula because the formula generates the same number as the experiments do, but it doesn't really explain what's going on. So the mystery deepens. Okay, so what does n represent in this formula, if that's the case? And why is it that when n is 3, it gives you red, 4 is going to give you blue-green, 5 and 6 is going to give you the shades of violet? Let's get back to the blackbody radiation. Blackbody radiation, when it is plotted, it's going to look like this. All right, so you end up getting a bunch of hills, and that's what it looks like. Okay, looks like you have a bunch of hills, and K represents the temperature in terms of Kelvin. And notice that when you increase the temperature, the peak of the radiation is going to shift from left to right. That's what it means. This means the intensity that you're looking at, how vivid the colors are, in essence. And then when you increase the temperature, the peak is shifting from left to right, meaning that the peak color is going to shift from red towards the blue end. So there's a shift in the peak color from red towards the blue end. All right, so experimentally, when you plot the numbers, this is what it looks like. And so this is known as the blackbody radiation curve because you end up getting these curves. So the question is, why is it that whenever something is heated, it's going to glow in red at first? And then notice that when you increase the temperature from here to that, there's going to be a shift in color towards the blue end. No one knew how to solve this problem until this guy came along. His name is Planck. It's not Planck, it's Planck. This guy is once again German. If you hear a hard A, that means that it's German. All right. This guy is the guy who was able to solve this problem. His name is Planck, and he was able to solve this problem by assuming that the energy is quantized. So what's the meaning of quantization? Quantization simply means energy is coming in small chunks. So energy is not continuous. It's simply is coming in small chunks. How did he know that he actually solved the problem? He knew that he solved the problem because this is your blackbody radiation curve. All right, the little dots that you're looking at are the data points, and then so the curve looks like that. So when you connect the data points, you end up getting the plot. His theoretical number, the theoretical shape that he was able to generate using his mathematics matched this curve with 100% exactness. All right, so his curve ended up matching the data points with 100% accuracy. That means that whatever the theory that he came up with was accurate. Except his theory, just like every single theory in physics, is sensitive to assumptions. The underlying assumption of his theory was that the energy came in small units. These small units of energy are known as quantum. And this is known as the quantum theory. So he was able to quantize the energy. He was able to break the energy into small units. So what that means is when you drop a ball or roll a ball down, you know that the gravity is going to take over. So what does gravity do? Gravity is going to take the stored energy, the potential energy, it's going to convert it into kinetic energy, which means that this thing is going to speed up. And it's going to keep speeding up continuously. What Planck's assertion is that what looks continuous happens in extremely small step sizes. All right, so which means that whatever you're observing here is going to happen in small step sizes. And the step sizes are extremely small. How small? This small, guys. You got 33 zeros before you hit the first number. All right, so this is almost like 0. Numbers are so small, the step sizes are so small. From our daily experience, it looks continuous. In reality, what's happening is the potential energy turns into kinetic energy in very small step sizes. Step sizes are so small that you don't even notice it. The other thing that means is the universe is quantized, which means that the reality as we experience it is not analog, it's more digital. Which means that the universe is, it's like a video game. That's what it means. All right, all of a sudden, we're back to Matrix. All right, so this is Planck, and he introduces the H into physics that's known as the Planck's constant, named after him. But that's the quantization number. It introduces a step size to the energy. It takes the energy and then turns it into particles, known as quantum or quantum. All right, so it solves the problem in 1899. And then he presents it in 1900 and then publishes it in 1901. And that was the Nobel Prize in 1918. All right, the stuff that you guys are looking at is written on the site. Everything has been plagiarized from Wikipedia. And I know it's plagiarized because I'm the one who did the plagiarizing, and I know my source. I know it's Wikipedia. All right. So, and when does copying information become plagiarism? It becomes plagiarism when you actually present somebody else's work as if it's yours, and that's exactly what I'm doing right now. It's my own PowerPoint. I just end up copying and pasting stuff from a source known as Wikipedia, evidently not available to everyone, surprisingly, because most people would be using it. And I'm presenting it as if it's my shit because I'm not giving credit to Wikipedia in writing. That's called plagiarism. All right. Now that I made my point, and I already told you that it's not mine, it's from Wikipedia. The thing I love about Wikipedia is this. It's compact information. You just get through it. You see the picture of the guy. His name is Max Planck. It's not Max Planck. It's Max Planck. Once again, this guy is German. And then all the relevant information is contained here. So evidently, quantizes energy in 1899. Then go forward, he presents it in 1900, and then he publishes in 1901, and wins the Nobel Prize in 1918. This is what I fucking like about Wikipedia. Just bare minimum facts. At the same time, it's highly misleading. And this is the second thing that I hate about Wikipedia. One of the things that I love is compact information. That's also what I hate about Wikipedia. It's compact information, not reflective of what's going on in reality. You have to kind of dig in to see what the fuck is going on. When I say what the fuck is going on, something is going on here, which is really disturbing. This guy solves a problem in 1899. The biggest problem in physics was solved in 1899, guys. This fucking problem persisted for 100 fucking years, and this guy solves it and sits on the information for about a year, and then he presents it and then does not publish it another year, and then somehow magically wins the Nobel Prize in 1918. Why is it that this guy is sitting on the biggest discovery for 2 fucking years without publishing it? You say that stuff is missing from Wikipedia. You don't get that stuff. When you guys are cheating from Wikipedia, and all of a sudden the stuff that I'm looking for is not there. You guys get the essentials right. The rest of it is usually not there. What's missing here is this guy is sitting on this information. There's no reason to sit on information like that. This is gold. This is one of the biggest discoveries. In fact, physics is about to be revolutionized because of what this guy did. And he's just sitting on it. Why is he sitting on it? And then why is he just not publishing it? Instead, he just presents it and then sits on it again 1 more year. And then why is that there's a 17 years later, he wins the Nobel Prize? What the hell is going on? Something weird. Something is fishy. What's going on here is this. As soon as he introduces the Planck's constant, as soon as he quantizes energy, he knows that there's no way he can publish his results as is. Because if he were to publish his results as is, he would definitely, most likely, with 99.999 certainty, he will lose his job. All right, because something weird about his result. Assuming that the energy is quantized means the same thing as light has a particle nature. It's the exact same thing. If you assume that the energy comes in particles, that's the same thing as saying that the light comes in particles. Nature of light is a particle nature. Up until then, every single fucking experiment that they end up doing prove that the light is a wave. We discussed that. Every single experiment. Not only do we know that the light is a wave, we also know that it's a transverse wave. This guy is a well-established physicist. He's one of the best in this field. He's not going to come out and say, assuming that the light is a particle, we can explain the blackbody radiation.